And the session is going to be uploaded later to YouTube, so everybody that's asleep now can catch up later. I would like to remind the audience that during the science talks, you should keep yourself muted and your cameras off so we don't take up too much broadband. If you have any questions, then you can raise your hand via the reactions button, or you can type them into the chat. You can ask your question live when the chair, so me in this case, calls on you, or you can just type into your chat question that you want to, that you want us to read it out. So for the speakers, a quick reminder, contributed talks take 15 minutes, invited talks 15. Both have 5 minutes questions. And I will give you a 2-minute verbal warning. So I will appear as a voice from the heavens. This day is the day that's geared towards the morning in the Americas. So good morning to everybody in America, south or north. Good afternoon to everybody a bit closer to the meridian. And good evening and good night to everybody in Asia and Australia. We have a very diverse program today, and we have 5 contributed talks in this first session. We're going to start in 3 more minutes. So let's wait a bit so we can keep time with our schedule. So again, a reminder for everyone to please mute yourself and turn off your camera, so we're not taking up too much broadband. All right, people are entering. All right, so people are stopping to trickle in. The trickling in is at a steadier pace. Let's put it that way. So please, everybody, follow our code of conduct. You can find it on the website. Also, I forgot to mention earlier, if you have any other questions that can't be asked live, or follow-up questions, or maybe you're watching this in the future and you have any questions to our speakers, there's a dedicated Slack channel, day 4, a very descriptive, and any questions can still be asked there. Okay, so Steve, the time is nearing. Can you please go ahead and share your slides?
Sure.
Our first contributed talk of this session, perfect, Steve. Our first contributed talk of this session is by Steve Goldman at the Space Telescope Science Institute. And he will tell us all about the census of dust-free and dust-producing metal-rich thermally pulsing AGB stars in the Andromeda galaxy. Okay, so Steve, I will give you a 2-minute warning. After 13 minutes, I will reappear as a voice from the heavens. And well, please go ahead.
All right, thanks, Marie. And thank you, Marie and Thaisa, for putting this whole thing on. So my name's Steve Goldman. I'm a postdoctoral fellow at the Space Telescope Science Institute. And I'm going to be talking today about the work I've been doing with my supervisor, Martha Boyer. So before I get into what I've been working on, I wanted to kind of explain how I got here. I've been trying to focus on understanding the effect of metallicity on AGB evolution, mass loss, dust production. And the way I've been trying to do this is go to more and more metal poor environments. So I started my PhD in the LMC, and I've worked all the way down to LEO P, where we've recently discovered the most metal poor, dusty AGB stars of both oxygen and carbon rich chemistry. And so we thought it was a good time to maybe go to a more metal rich regime now. So in terms of large samples, we're somewhat limited to the Magellanic Clouds, where we have complete large samples that are robust. And so we've been slowly working down by observing metal poor dwarf galaxies and globular clusters. This is work done in large part by Martha Boyer with the dustings and Lovett surveys, as well as a bunch of work done by people like Libby Jones and Patricia Whitelock, John Menzies, and Ian McDonald. And so these are small samples in globular clusters of dwarf galaxies, but we're slowly building them up. In the metal-rich regime, we're still working on building up those samples. So this is a figure from Martha Boyer's paper showing metallicity versus the log age, and showing the parsec colibri models and the different boundaries of the carbon and oxygen-rich chemistry. So here the oxygen is blue and the carbon is red. And it's still unclear where these boundaries are, and some models disagree on where they are. So we want to try to uncover these boundaries, but also to try to figure out if there's a ceiling for carbon star formation in the metal-rich regime. And so I was happy to see that Julia Cinquegrana is working on this. And then lastly, we want to understand the effect of metallicity on dust production. And so this is a figure showing the average dustiness of stars in these metal poor dwarf galaxies. And there's still a bit of scatter, and we're still lacking data at supersolar metallicities. And so one of the ways you can try to tackle this problem is by going to the Milky Way, of course. We heard about both Death Star and NESS, and those nearby samples that are looking at more complete samples of nearby AGB stars. But one of the disadvantages of that is that we have to look through the disk, and so we can't see the dustiest stars because they're obscured by interstellar extinction. And then also with in terms of distances, a lot of them are unclear, and Gaia will be unlikely to detect them because one, Gaia has optical filters, and so the dustiest sources will be missed. And then also their convective cells make things more complicated. And so the more distant sources are hard to get distances on, which you need for things like luminosities and mass loss rates. So one of the ways you can tackle this problem is by going to M31, Andromeda. We have the advantage of a wealth of archival data. It's a much larger sample, and it has a known, relatively uncontroversial common distance. But it is more distant, so it's harder to resolve these populations and to get complete samples. So the Hubble did the FAT survey. It's a huge Hubble Treasury survey from the UV to near IR, where they resolved 120 million stars. And so we have this Hubble archival data, and we also have data from Spitzer with IRAC and MIPS from 3.6 micron all the way out to around 24 micron is what we can still use. So we have all this data, and we used it to classify the AGB population within this FAT footprint. And so this is showing the spatial distribution of all those AGB stars. In total, we have around 370 thermally pulsing AGB candidates. And using the Spitzer data, we also classified some sources exclusively with the Spitzer data and found around 5,000 really dusty AGB stars. So we used some near infrared wideband filters for this classification. So on the left is showing a couple of the color and magnitude cuts that we made. We made a bunch of other quality and color cuts to weed out the foregrounds and the other contamination. And then on the right is the HST data from all the sources we classified exclusively with Spitzer. And so these are showing what we're expecting, that the dustiest sources fall down into the right, where you're seeing more extinction. And we expect that these are real dusty sources, as they have a pretty uniform distribution across the disk. There's no concentrations around the ring in particular, which maybe you think that they're hotter stars hiding behind some dust, but we're pretty confident in these sources. But then again, Spitzer, we have less angular resolution, so there may be a little bit more contamination. So we have AGB sample, we have a dusty AGB sample, but also we have the benefit of additional medium band data that Martha did. And so we have chemical classifications for small regions across the FAT footprint. This is something that Libby was talking about yesterday, using 3 medium band filters that probe important molecular features. in oxygen-rich AGB stars and also the carbon stars. And so those are the three filters in blue. And then we also have in the bottom there in the gray is the F110 and 160 filters that we use to classify the AGB sample. And then the raggedy filters are the J and K. And so plotting these on a color plot, this is what you get, a beautiful separation of all the oxygen-rich stars in the top there in the blue region, the carbon stars falling to the right. We have the added benefit of all the foreground sources falling in that white region in the bottom left. When you move up into the left in this diagram, you get increased water absorption. So it's a way of spectral typing your AGB star if it's oxygen-rich. And then if it's dusty, it moves up into the right where you follow those extinction vectors in red and blue. And so we see, I plotted the dustiest sources in the LMC from Groenewegen and Sloan 2018 and where they would be on this plot. And so this is a lot of power for discriminatory power for finding these samples. And then also with the angular resolution of Hubble, you can weed out all the background galaxies. And so this is a really powerful method for identifying AGB samples. And so now that we have AGB stars, dusty AGB stars, and these chemically classified samples, we can start to study them individually. And so here is the spectral energy distributions of the oxygen-rich, the carbon-rich, and then the extremely dusty or XAGB stars. It's not a great name, but it fits on the plot. And so on the left, we see increasing water absorption for the brightest sources. These are all binned by their 3.6 micron IRAC magnitudes. And then the carbon and the XAGB samples follow what they did in the SMC or the LMC. And this is a figure I wanted to bring particular attention to because this is the infrared carbon star luminosity function. So here I'm showing the 3.6 micron data from the LMC and SMC in the green and the orange, and then for the M31 carbon star sample in the blue, and then the full M31 sample where we have data in the gray. And so what this is showing is essentially the boundaries in luminosity or mass for carbon stars. We're only complete, I'm just showing the 90% completeness level there. We're only complete on the upper ends, but if you believe the lower end, it's a clear indication that there's a more narrow range of metallicities and assumed mass for the carbon stars, which is what we expect in a more metal-rich environment. And then when we look at a color magnitude diagram of this data, you can see that for the LMC data on the right, there is a clear population of orange sources that are the carbon stars in that box there, that rectangle. And for the M31 data, in the pink there, we're kind of missing sources. In the background is the LMC data in black, but for the pink data, we're kind of missing these carbon stars, which is again what we expect in a metal-rich regime. Okay, one other thing we have in this sample, which is really powerful, is we have cluster data. And so in these measured clusters, we've measured spectroscopically metallicities. We have ages for a lot of them. And so we can identify AGB populations in these environments and use them as calibrators for stellar evolutionary models. So we have a range in terms of the age, mass, and metallicity of these clusters. And so now we can start to go back to this diagram here and probe regions close to these boundaries with different clusters. And so this is something we applied to do with James Webb in cycle 1 and just didn't make it, but we're going to apply again in cycle 2. And then lastly, I wanted to bring up the fact that we have data covering the bulk of the emission of these AGB stars in each of these filters. And so what we can do is SED fitting to some degree. So this is one of our cluster sources where I fit the SED with a package that I developed called the Dusty Evolved Star Kit. It is a package that's fully documented. It has unit and regression testing. So if it breaks, I'll know. Command line and Python interface. So if you don't understand Python, it's very simple to use. It's peer reviewed by other software developers and published in the Journal of Open Source Software. And it has a lot of commonly used grids, including Graham's, Bernani's 2019 dust growth models, and then a bunch of other grids with varying dust properties, including one I recently made inspired by Martin's more of dusty code. So we're tackling the problem of having a limited sample in the metal-rich regime by trying to use M31, but also Milky Way sources. And then also for the metal-poor regime, we're slowly building up samples, but we're still lacking sources because they're small, small dwarf galaxies and globular clusters. One other thing I wanted to mention is that we noticed that for some of these AGB stars, they show UV excesses. So this is data where these sources were classified with the Hubble data. And they also show the fat data in the UV is quite bright. And on the right here, I'm showing that they are also quite variable. So because of how the survey was designed, we can get some amount of variability information from the survey. And here I'm showing the variability index, or the standard deviation of the magnitude over the average photometric uncertainty. And so some of these are both bright and varying on short time scales. And so these might be interesting candidates for binaries or symbiotics. And so we're gonna look into this. And then all of that also got me down the road of looking into symbiotics. And this is a poster that's in the poster hall where I'm leading a couple of programs on Hubble and Sophia with the help of Ravi Sankrit and others to look at HM Sogeti, which is a post-outburst symbiotic system, which had a nova-like outburst in 1975, and now we're looking at it again in the UV and IR. So that was a lot to take in, but I am happy to answer questions if we have some time.
We have plenty of time, Steve. You kept well within the time limit.
Fantastic.
So that's great. So if anybody has some questions, please raise your hand via the reactions button, or you can type it in the chat. That's also a possibility. So far, I see someone clapping, but no raised hands or messages. I have a question for you, perhaps a stupid one. Is it possible to constrain the dust composition as well from your SEDs, or is that what you need JWST for?
So we're going to try to do some SED fitting to understand the dust budget in general, but a lot of this photometry is multi-epoch. And so we have different timed data for the infrared and the optical. And so it makes SED fitting, which is already quite hard, even more complicated. And so we're trying to make estimates on dust budgets in general, but the composition will need James Webb, I think.
All right, thank you. Yes, we have a question. Please go ahead and unmute yourself, Joe.
Hi, Steve. So for the UV access, can you will you be able to identify the if it's a symbiotic star? Will you be able to identify the source of the accreting star, like if it will be a main sequence star or a white dwarf?
Yeah, so that's something we're working into. It's a little bit outside of my field, but I've been learning a little bit more about it. And it's, from what I understand, a little bit more complicated to determine if it's an intrinsic or extrinsic UV excess. So whether it's chromospheric related or if it's a binary companion. And so we can do things by, we can look in the UV for particular lines that are good indications of confirmation of a binary. But in terms of the properties of the companion, I'm not sure about that. Someone else will be able to answer that, I'm sure, though.
Yeah. Thanks. So there is also a possibility that this variation or UV access is intrinsic to the pulsation of the AGB star.
Sorry, could you say that again?
You mean there is possibility that this UV access is related to the pulsation of the AGB star?
I'm not sure if it's related to pulsation. I think it might be chromospheric. This is a little bit outside of my topic, though.
Yeah, sure. Thanks.
Thanks. Theo, you also had a question?
Yeah, thanks, Steve, for a nice talk. So I have a question about something that you mentioned quickly, but unless I missed it, I don't think you came back to. Is this the limit on for the production of carbon stars, the limit on metallicity? where do you expect the limit to be, more or less from theoretical models, and what type of environments would you look for stars to probe that?
That's a good question. That's probably a question that either Amanda Karakis or Julia Cincograna can answer. But in terms of observations, Martha went back, and after we did this, she got more time on Hubble to probe some more of these medium band filters closer into the galaxy center, but also farther out and in M33. And so that's what we're going to do.
Okay, thanks.
All right, and we have another question by Libby. If you would like to answer your question, well, ask your question live, go ahead. If not, I will read it. So the message in the chat is metallicity gradient in the M31 disk. Can you trace a gradient in the amount of dust produced by the stars or the amount of C, M-type and X AGBs?
Great question, Libby. One of the complicating factors is that as you move to the galaxy center, we have some completeness issues, and the ability for Spitzer to pick them up closer to the galaxy center it's kind of hard, and so it's hard to say anything in concrete about any metallicity or distance gradients because of the completeness issues.
Okay. Are there any other questions? Please raise your hand or type in the chat. If not, we can move to our second speaker. If you think about another question to ask Steve, then please go to our Slack channel, day 4, where all the questions can be answered asynchronously. So Steve, please stop sharing your screen. And Juan, please start sharing your screen. We will wait a few minutes so we're on time, more or less, since people might drop in just for your talk. Who knows? With these virtual meetings, it's best to keep on schedule. So Yuan will tell us about the fate of AGB winds in massive galaxies and galaxy clusters. And she is from the University of North Texas. Looking forward to it.
Thank you.
Well,
so first,
yes.
I want to thank the organizers for having me here. I usually work on galaxies and galaxy clusters, but over the past few years, I've become very interested in AGB stars, and I think they hold a key to a very interesting puzzle related to dust in massive galaxies and galaxy clusters. And I have been learning so much from watching all the talks at this conference, and I hope to learn more at the end of my talk today. You will see there is a call for help. So a little bit of a background. Most massive galaxies in today's universe look red and dead in the optical. They look pretty boring, but it doesn't mean that nothing interesting is happening there. So if we look at them in the X-ray, we see this hot gas that's the virialized halo gas with temperatures of a few times 10 to the 6 Kelvin. And you can see that this gas is very disturbed. And we think that that's because of the feedback from the supermassive black hole in the center of the galaxy. The interstellar medium of massive galaxies is often multi-phase. So in about half of the nearby massive galaxies, we also detect a much cooler component. So for example, here you can see these red filaments that can be detected in the H alpha. So that's tracing gas with temperatures of about 10 to the 4th Kelvin, so much cooler than the X-ray gas. And there's also a low-level star formation, which presumably happens in some of these filaments. And scatter feedback from evolved stars is very important in these massive galaxies. For example, the total mass return from evolved stars in a typical elliptical galaxy over 2 gigayears of time is about equal to the total amount of gas that's available in the galaxy. And it provides more than enough fuel for the star formation in these galaxies at the level that's detected. More importantly, AGB stars produce the dust that we see in these galaxies. And the situation is similar in the most massive galaxies that are found in the centers of galaxy clusters. So again, on the left-hand side, you're looking at an X-ray image of a nearby galaxy cluster called the Perseus cluster. You can see the very disturbed hot gas as a result of feedback from the supermassive black hole. And then if you look at the same cluster in H alpha, you see these really, really beautiful filaments that can extend out to tens of kiloparsecs. Now, just to remind you, the temperature contrast here, the left-hand side, you're looking at gas with temperatures above 10 to the 7th Kelvin here. On the right-hand side, you're seeing gas with temperatures of about 10 to the 4th Kelvin, or even cooler because there's also molecular gas in a lot of these filaments. So the question that everybody would ask right away is, how do you get this cold gas out there? One idea is that there's some cold gas reservoir in the center of a galaxy or a galaxy cluster, and then some feedback process can push this cold gas out to a large distance. We don't think that this is happening in massive galaxies or galaxy clusters because there's not much of a cold reservoir of gas in the center. And so we think this is probably happening in galaxies like our own Milky Way, where stellar feedback is driving multi-phase galactic winds. But in galaxy clusters and massive galaxies, most of the people in the community think that the cool filaments cool out of the hot intercluster medium due to thermal instability. So these cold clouds form in situ. In the past decade or so, there has been a lot of theoretical and numerical studies on the formation of these multi-phase filaments. And I've highlighted a few papers that I was part of. The majority of these works are based on the idea that the cold gas forms out of the hot gas due to thermal instability. So to give you a sense of how that might work, here's my own numerical simulation of a Perseus-like galaxy cluster with a black hole sending out jets in the center. So on the left-hand side, you see how the jets are influencing the surrounding hot gas that you can see in the X-ray. You see all these ripples, which are shock waves that are heating up the surrounding gas. Now, if we look at the cold gas, then we see that under the influence of the jets, the hot intercluster medium goes thermally unstable and it cools into these cold blobs, which then feed the black hole and then causes the cluster to go through cycles of black hole feedback and cold gas formation. So I thought my model was fantastic and it explains a lot of observations. I was happy with it until someone pointed out to me a very fundamental flaw in my model. And in fact, it's not just my model. There is a big problem with almost all existing models based on thermal instability. And that problem has to do with the existence of dust in these filaments. Observations tell us that all of these filaments, all of these cold filaments found in massive systems are dusty. And according to Donahue et al., the dust grains are also similar to those of normal star-forming galaxies. And there are even PAH molecules there, which are extremely fragile. This is very puzzling because the hot gas that we see in the X-ray is dust-free, because dust sputtering time is very short in those harsh environments, and we all know that. And we can also look at sputtering time compared with the cooling time of the gas. So the plot here is showing you dust sputtering time divided by gas cooling time as a function of halo temperature. And the orange line is showing you what happens to the biggest grains we can think of. And the blue line shows what happens to a typical dust green. As you can see, in all massive galaxies and galaxy clusters with temperatures above half a keV, even the biggest greens cannot survive longer than the cooling time. What that means is, even if you keep replenishing the hot intercluster medium with fresh, with newly made dust greens, the dust greens will be sputtered by the time the gas can cool. Gas be dusty. I guess now the question is, how do we protect the dust so that it never gets exposed to the hot gas? And since most of the dust is made in AGB winds, the question turns into, how do we protect cold AGB winds in massive galaxies and galaxy clusters? Now, before we can answer that question, we have to ask, what does an AGB wind even look like in a massive galaxy? Now, we know an AGB wind looks kind of like this in our Milky Way, and we've heard lots of beautiful talks on these objects this week. But I know that this is not what a typical AGB wind would look like in a massive system. Why? Because stars are moving really, really fast there, and the surrounding gas is very hot. Stars in our own Milky Way that move typically very slowly, and the surrounding gas is cooler. Now, there is one exception. That is Mira, the wonderful star. It is a star that's moving really fast with velocities above 100 kilometers per second through the local bubble, which is a local hot environment. And here is a galaxy UV image of Mira, and you can see this really beautiful long tail, about 4 parsec long. This we think is coming from the molecular hydrogen in the tail. So what's happening to Mira is that as Mira moves against the hot background, the stellar wind from Mira collides with the hot ISM, and the ramp pressure of the hot ISM pushes the cold stellar wind to the other side to form a tail. So Mira is not a typical star of the Milky Way, but Mira's situation resembles what would happen to a typical AGB star in a massive galaxy or a galaxy cluster. More than 10 years ago, Joe Parrott and Joe Bragman did this beautiful 2D simulation of an AGB star in the outskirts of a elliptical galaxy. And you see that it does have a tail that kind of looks like Mira. And what they find is that part of that cold stellar wind leaves their simulation domain as a laminar flow. And that suggests that some of the dust can be preserved, which is very exciting to me. However, if I rerun their simulation in 3D, I see that everything gets mixed. I don't see that cold laminar flow anymore. And this is probably because there are instabilities that just don't grow in 2D, but can grow in 3D. But just in case there's anything wrong with my simulation, I also did a simulation that's tailored for Mira. So I used the exact condition of Mira, and that's my Mira, simulated Mira. And then I also did a simulation of an AGB star. And so the one I showed you earlier is an AGB star in the outskirts of elliptical galaxies. And here's an AGB star in the center of a elliptical galaxy. They all look more or less the same. Then I figured out that analytically, all Mira-like stars should look the same. They should all have the same tail to head ratio of about 4 in the absence of radiative cooling. Now, if I do allow cooling to happen, then suddenly my Mira grows a much longer coat tail. And that also happens to the AGB star that I put in the center of a elliptical galaxy. It doesn't happen to the star that I put in the outskirts of a elliptical galaxy, even though there is radiative cooling. So what I found out is analytically, the cooling time of the tail of the mixed gas is inversely proportional to the ambient pressure. So in the outskirts of elliptical galaxies, the pressure is just not high enough for cooling to be important. But if you move the star to the centers of elliptical galaxies, then the pressure is high enough so that some of the mixed gas can cool. And the same thing happens to Mira. And so I think that the tail that we're seeing in Mira is actually not just from Mira itself. Some of that gas is actually the cooled hot in ISM. So my tail of Mira has more or less the right length. I've also compared the velocity of the tail as a function of position to the observations of Mira. Again, I find excellent agreement between my simulation and the observations of Mira. So that was good news, telling me that my simulations are pretty good. However, you can see that my Mira is losing its cold gas. And so what that means is if I put an AGB star in the center of a massive galaxy or a galaxy cluster, very quickly, dust is going to be destroyed. So even though dust is preserved a little bit longer than high pressure environment, it's still not long enough. And that is a problem. So to quickly summarize, in the absence of radiative cooling, all Mira-like AGB tails look pretty much the same. And radiative cooling is important in high pressure environments, such as the local bubble and centers of massive galaxies and galaxy clusters. And hot gas can cool onto AGB tails due to mixing in high pressure environments, for example, in the situation Mira. However, current models still cannot explain the existence of dust in the filaments in these massive systems. And so I think we need help from other communities, for example, people here with knowledge of AGB stars and dust. And so if you have any ideas, please let me know. Thank you.
Thank you for your very interesting talk. Lots of beautiful simulations. 2 people are applauding, so I'm not the only one thinking this. If anyone has a question, please raise your hand or type a question in the comments. All right, we have a question. Kang, please go ahead and ask.
Hi there. Thank you very much for the really interesting talk. I just wanted to ask about so the same kind of your problems about dust in massive systems. Have you ever considered looking into Wolf-Rayet stars as well as the Miracellae types?
I have not. I didn't know Wolf-Rayet stars also made dust.
I'm not too sure, but I know that they are like really young and massive systems as well. I don't know if that is something of interest as of yet.
I haven't thought about it.
Modeling.
I mean, presumably you could model anything, right? Yeah. So I know that there are people who are modeling Wolf-Rayet stars orbiting the Milky Way black hole. So Sean Ressler did an interesting work. Actually, it's a series of work, and he was looking at how the stellar wind is accreted onto our own Milky Way's black hole. So that's interesting. It's not exactly what right now I care about dust.
All right, let's move on to another question.
Thank you very much.
Thanks for your question. Shazreen, you also have a question. Please go ahead.
Yeah, actually, I have a comment regarding the previous question and the question. Yeah, so Wolf-Rayet stars do produce dust. When they're in binaries, the collision between the stellar winds actually creates conditions where we actually see it. You can see this beautiful images of the Pinwheel Nebula, for example, and that's seen in dust by Tuthill. So you can have a look at that. The other option for producing dust in these hot systems would be something we mentioned with Libby yesterday, and that's looking at dust formation in AGN. So there are some nice models now by Aka, Sarangi, and Eli Dweck, I think 2019, that you can have a look at, where they actually form the dust in AGN disks. And they form a lot of it. So that's really, really a useful source of dust if you're interested. I mean, I'm partial to Myra, so I like this, and I think we should, let's chat more about how we can fix it for Myra.
Yes,
but
please.
Certainly, and the question that I had was about the radiative cooling that you include.
Mm-hmm.
What do you do for the radiative cooling? What kind of processes do you include? Do you include molecular cooling, low temperature cooling?
So it's the sort of the standard ways simulators do radiative cooling. Nothing fancy, just tabulated.
Yeah, because I think that's one of the things we did for our Betelgeuse bow shock simulations and forming these tails was to include low temperature cooling. So usually the standard cooling goes down to 10,000 Kelvin. That's typically what people do.
We do have a cooling curve that goes down
below
to
that.
a few hundred Kelvin. Yeah.
Okay. All right. That should be good. But let's chat more about that. Sorry.
No problem. There's still some time. Definitely post those papers.
Great. Very nice.
Yeah, definitely post those papers in the Slack. Shazrina, I also would like to check them out. Theo, you also have a question.
Good. I'll do that.
Yeah, so I thought it was a very interesting talk as well. It's really good to see this cross between fields. And so actually, Shazreen asked my question. I was going to ask about how good of a handle you have on the cooling, but I also have another one. So I think we are slowly acknowledging, or maybe not slowly, I'm just the slow one, that a lot of systems produce a lot of dust very suddenly from binary interactions. And would such a very sudden production of dust and mass loss affect your results if you expel, let's say, one solar mass over a few years or 100 years? Would that help keep the gas cool, you think, or would it not make a difference?
So I don't know what kind of binaries you're thinking about. So if all of the filaments, the coat filaments, are dusty, either you have a lot of sources that make dust, even though the dust is short-lived. If you keep throwing dust out there, then it might work. Or you have fewer sources, but the dust survives longer, right? So if you can think of a way to make dust out of ordinary stars, then that would help. So my approach is first to see if somehow we can just use the classical approach, just the standard AGV wind, and see if we can save the dust in the wind. So I haven't thought about binaries, but yeah, maybe we should talk more.
Yeah, exactly. Oh, yeah, we can talk more about it. Yeah.
You're muted.
If I can just quickly add, while I don't hear Marie, I'm not sure if there's something wrong with my connection, but Anita's point in the chat
was talking about muted.
Anita's point in the chat is really good. That's one way that we can save it. So what Theo suggested is binaries, because Myra is a binary, and so that's another way that we can do it for the AGVs, but also clumpiness. So we do find dust in a lot of hostile environments.
Okay. Now I'm not muted, but Shazreen, okay, she's muted, so you turned into a robot for a bit. Thank you for your very interesting talk. There's definitely a lot of discussion going on. Now it's time to go to Anna's talk. So if you could please stop sharing your screen, and Anna, go ahead and share yours. All right, I can see you. I can hear you. Please go ahead.
Yeah, thank you, Marie. And thank you to the SOC for giving me the chance to speak here today. And what I want to speak here today about is barium stars. I want to show you the most recent observational constraints that we have about these objects, and I want to suggest how we can use them to learn about their progenitors, which are AGB stars and AGB binaries. But before I enter into the topic, I want to throw this reminder here for everyone. I want to remind you that stellar masses are a fundamental parameter in stellar astrophysics, but that they are very difficult to measure. So we should always be careful with this. The initial mass of a star is going to affect its evolution, its internal structure, the final fate, and as it's been discussed already in this conference, also the chemical production. And I'm sure I'm forgetting many other aspects that are strongly affected or even determined by the mass of the star. However, as I said, it's a challenge to determine these masses, and it's even more challenging in the context that we are discussing in this conference. If you want to determine the mass of an AGB star, you need to deal with messy, huge convective atmospheres. You need to deal with mass loss and with pulsations and all these kind of things. Even in the best case scenario, if you want to use binarity to help you, because when you have a star in a binary system, determining masses or getting information about these masses is a little bit easier. Even in this case, it's not favorable for AGB stars because binaries hosting AGB stars are wide. And then to get these orbits and to get this mass information, you need a strong and huge observational effort. So what I am proposing here is to use the progeny of AGB binaries in order to learn about the AGB phase. And this is not a new idea. It's not that I'm proposing this here for the first time. There's been a huge amount of work in the last decades studying the progenitors of AGB binaries in order to learn about the AGB phase. And these progenitors are post-AGB stars that have been were discussed on Monday and Tuesday, I think, barium stars, CH stars, CMP, S stars, and technetium-4 S stars. I am not going to enter into all these families. I think most of them, if not all, have been mentioned or discussed before, advantages of speaking almost at the end of the conference. So I am going to focus only on the barium stars. They have also been mentioned, but I'm still going to remind you where they, what they are and how they are formed. So barium stars are these systems over here, main sequence and red giant stars, with a strong abundance on the surface of S-process elements. These S-process elements are produced by the slow neutron capture process of nucleosynthesis, and this nucleosynthesis process is known to take place inside AGB stars. So these elements were not synthesized in the barium star itself, but accreted in a binary system, in a mass transfer episode from a former AGB companion, this guy over here in my cartoon. This former AGB companion evolved off the asymptotic giant branch star and is now a cool white dwarf that we cannot detect in most systems. So this is the type of systems that I am looking at. This is how they look in a not to scale, of course, cartoonish kind of way. And what we want to do is, as I said, using the observations of these objects in order to learn about their progenitors. So what I'm going to show you now is the most recent observations that we have collected, done, improved concerning these objects. And then I will discuss how we can use these observations further. I'm going to start with the orbital properties of barium stars. One of the main phrases in their definition is that they are binaries. They are main sequence. I left here the cartoon to remind you the kind of objects that we are looking at, main sequence and red giant stars with a wider companion. And as I mentioned already, binaries that host or have hosted an AGB star, unless they go through common envelope evolution, are going to be wide. So these barium stars are wide binaries. This example that I am showing over here is the main sequence barium star and has a period of about 6 years. So in order to get the radial velocity curve that I'm showing you here and to fit it and determine the orbital parameters, we need a lot of data. The main data set that we worked with was these points over here, the radial velocity obtained with the Hermes spectrograph that has been monitoring the radial velocity of evolved wide binaries many years already. And we combined this with older radial velocity monitoring programs of barium stars or other archival data, including SALT for the southern objects. So with all this data, we can show you the family picture of the barium stars. In orange, the main sequence ones, and in dark and in black, the giants, published in a paper by myself, led by myself in 2019, and one by Alain Jorrison, respectively. So in these pictures, you have the periods of the orbits in the y-axis, in the x-axis, and the eccentricity in the y-axis. So the two main orbital parameters that we wanted to know. And I am not going to enter farther into the orbits and how we can use this, but I do want to mention that this is already a strong observational constraint for models, because it's a known problem that binary evolution models that involved mass transfer or binary interaction with an AGV star don't properly reproduce the orbits of the progeny of barium stars, post-AGV stars, and so on. So there's been a lot of work in this framework as well, but I'm not going to describe it now. What I'm going to do, we ourselves, I almost forget to advertise our own work. We also use these orbits in order to learn about binary interaction, but not in the AGV phase as I was proposing, but in the red giant phase, because main sequence barium stars will evolve into giant barium stars, and in between, in this path, there can be a binary interaction between the barium star itself and the white dwarf. So a second stage of binary interaction for these objects. But as I was saying, what I want to focus on concerning the orbits is the mass function. The mass function is this expression that I'm showing you over here, and that relates the orbital parameters, eccentricity, and period that we have here, and the semi-amplitude of the radial velocity curve that I showed you in the previous slide. And in this expression, you get this wonderful number, and it relates with the inclination of the orbit and the masses of the two components. So this is the mass of the primary of the barium star, the one that we can see. So we can constrain these easier than the rest. So let's go for it. In order to determine the masses of these barium stars, we built a Hertzsprung-Russell diagram. And we did this for both the main sequence and the giants as well. And again, a lot of data and a lot of work in a single plot. We use Hermes high resolution spectra in order to determine the stellar parameters accurately, Mach model atmospheres, Gaia DR2 distances, and starable evolutionary tracks computed specifically for this sample. And by comparing the location with the tracks, we could also determine their masses. So these are the mass distributions of the main sequence in orange again, and the giant barium stars. And you can see that there is a small difference. You could probably also spotlight this from the HR diagram, but we think that this difference between the mass distributions of the primaries is caused by an observational bias against more massive main sequence barium stars, and we are working on solving these at the minute. So we have M1, we can go back to our mass function, we have the orbital information, we have the mass of the primary, and we can now work our way towards the mass of the secondary, that is the one that can teach us about the AGV star that polluted these objects. So we can proceed now in different ways. We can assume our inclinations, because the spectroscopic binaries don't give us information about the inclination, unfortunately. So we can assume that our sample of binary stars are randomly distributed on the sky and find the best fitting distribution of secondaries that fit our data. But additionally, for this type of post-mass transfer objects, it was proposed that this ratio over here that concerns the masses of the two components, it's a very narrow distribution or even almost constant. This is a specific for this type of objects, and it's a further assumption that we can take. So we put all these data and all these assumptions together and managed to get a wider companion distribution, mass distributions for the wider companions. Again, in orange, the main sequence Barnum stars, or the wider with main sequence Barnum stars, and in gray, black, the giants. So these are mass distributions. These are not absolute masses. There are further tricks that you can impose on this work in order to estimate a mass, but it's more assumptions that we are adding. So we wanted to do the opposite. We wanted to remove assumptions and try to include as many observational constraints as we could. So we took a step back and decided to find those inclinations, to get those inclinations in order to not assume them, basically. So for this, we need astrometry, and these are the kings of astrometry on the sky. We have Hipparchus and more recently Gaia. Unfortunately, Gaia has not given us inclinations yet, but we can still use its data to try to get them ourselves. We could also wait until Gaia DR3, like the final DR3, but well, we decided not to. In the 2019 paper that I've been showing you all these in these old slides, we did this for 4 main sequence Barnum stars following the lead by Pourvois and Jorisen in 2000. For these specific cases, what we did was using the Hipparchus epochs, so the Hipparchus position of these stars on the sky, and impose our orbital parameters, so the orbital parameters that we determined for these systems, on the astrometric orbit in order to fit the inclination. So we did a lot of statistical tests to make sure that this was reliable and what we were doing a good job. And this was only the case for these 4 objects. That's why we could not get wider masses for any of the others. Again, we could wait for Gaia DR3, but we again decided not to. And what I am working on now is using a more complex model, which is described in these 2 papers by Rob De Rosa. And what we are doing is putting even more data together in order to get those absolute masses and not have to work with distributions. In this case, we are using the Hipparchus data, we are using the Gaia position, and we are using each single radial velocity point that we have. Instead of imposing our orbital parameters on the astrometric data, we are combining it with the radial velocity data in order to improve the orbits but get an inclination on the way. So this is work in progress. I cannot show you the results yet. I am very sorry for that, but I'm going to take you back to the other mass distribution that we had for these objects. And I'm going to just mention that the new one will look slightly different. I've seen some of these numbers, and it seems that the wide-wave companions of these main sequence Barnum stars is really picked, even more picked than this one, and centered in 0.6 solar masses. But as I'm saying, the models are running at the minute. I cannot give you numbers. So stay tuned. If you are curious, get in touch and we can discuss this further.
This is in 2 minutes.
Yeah, thank you, Marie. So I'm going to go back to my first slide, and I'm going to mention a couple of situations, circumstances, outcomes that we can get from these wider masses. So why the mass of these invisible and detectable wide-wave companion is useful for the community that meets here this week. So, for example, if we find that the companions of strongly polluted Barnum stars are different to the masses of the companions of mildly polluted Barnum stars, we could learn about the mass transfer process. We could learn about the nucleosynthesis inside these different progenitors as well. Additionally, if we combine the abundance pattern of the barium star, the chemical overabundance of these process elements with the mass of the white dwarf, as it was presented yesterday by Borbala, she is doing work basically this same thing that I am showing here. Watch her talk if you didn't. You can also learn about the AGB star and what's going on inside. Additionally, we can build an initial final mass function for these AGB polluters, for these AGB stars progenitors of these systems. And we could also get information about the mass ratio when we compare the mass of the AGB star and the mass of the barium star, the mass ratio that is needed to form these barium star systems. So this is all. I leave you here with my summary, in which basically I show you how we plugged in numbers in a very well-known equation in order to get masses for these invisible objects. So thank you for your attention.
Thank you, Anna, for your very interesting talk. We already have a question in the chat. Would you perhaps like to ask the question live? If not, I will read it out. I'll wait a bit to give you the opportunity. Everybody else, please go ahead and raise your hands via the reactions button. So no reply yet, I'll go ahead. Thank you for the very interesting talk. How much mass needs to be transferred to the companion in terms of the companion's mass or percentage of the companion's mass in your most extreme cases? Thanks.
Yeah, this is it's a very good question, and it's one of the questions that that concern these objects. It's not known. We find abundances, like overabundances, covering all the range that that you can imagine. So it's not really well known how much mass we are dumping into the companion. Additionally, the fact that we observe these overabundances in red giants that have gone through the first redshift tells us that either there was a lot of mass transferred, or that something didn't happen as suspected, because these abundances don't seem to dilute between the main sequence and the giant phase. So it's a very good question, and I'm sorry, but I don't have the answer for it.
Okay, thank you. Does anybody else have a question? Please go ahead and raise your hand. If not, I can ask you. I have a question, Anna. So you mentioned that there's an observational bias against more massive main sequence stars in your distribution plots. And you also mentioned that you were, well, fixing it. Could you tell me how you're fixing this bias?
I can go back to the plots. And so the problem with these orange stars missing over here is that they occupy this region in the HR diagram where chemical peculiarities are appearing for other reasons. So we enter the area of the A-type stars, and they are there are chemical peculiarities because of pulsations. There are chemical peculiarities because of magnetic fields. So I have the feeling that we have just missed them, that we have just missed this particular specific pattern. So I've taken high resolution spectra with Hermes as well for a sample of delta Scuti stars that were proposed in a paper by Simon Murphy to be, to have orbits close to the barium star systems. And we are looking for barium stars among those delta Scuti stars. We have found a couple of interesting objects, but again, work in progress.
Okay, interesting.
So I think we have just missed them.
Oh, yeah, they're not making life easy for you, as I understand. Thank you. If anybody else has some questions for Anna that they think of later or in the future, please ask them on the Day 4 channel on Slack. And if you could stop sharing your screen, please. And then there is a mishap for our next speaker. He's not able to connect to Zoom just yet. So there's a switch in the program, and Debora Schmidt will start her presentation now. So hello, Debbie, please go ahead and share your screen. And apologies for the sudden switch. Debbie is at the Franklin and Marshall College and will tell us all about the molecular material in planetary nebulae. Thank you, and please go ahead.
Excellent. Thanks very much, Marie. And thanks everybody for being here to listen to my talk. So as Marie said, my name is Debbie Schmidt. I'm an assistant professor of physics and astronomy at Franklin and Marshall College. And my research is in the realm of astrochemistry, so specifically molecular studies of evolved stars and primarily planetary nebulae. To date, over 200 different molecular species have been detected in circumstellar and interstellar environments, and these range from the really simple 2-atom molecules. So this table here is organized in terms of number of atoms per molecule. So simple 2-atom molecules are shown to the left here, all the way up to the really complex 10+ atom molecules, including C60 or buckyballs. And the molecular complexity of the interstellar medium is of particular importance because it can affect the potential for life to develop in the stellar systems that form out of this material. The problem is that models of the interstellar medium tend to have trouble with explaining the abundances of the different species that are detected there due to the low densities of these environments. And so this suggests that some alternate source of molecular material is needed to explain these abundances. Planetary nebulae offer up a good possibility, a good solution to this problem, because not only are most stars in the universe low-mass stars that will pass through the planetary nebula stage at the end of their lives, but these objects also provide about 80% of their mass or of their material to the surrounding diffuse interstellar medium. And so this means that if molecules are able to survive the planetary nebula stage, they could potentially seed the surrounding interstellar medium with this molecular material and provide more complex building blocks than just simple atoms from which to build up even more complex species. The problem, though, is chemical models of planetary nebulae have historically predicted that molecular abundances should be significantly depleted over the nebular lifespan of approximately 10,000 years. And this is due to the high energy radiation from the central star of these objects that can photodissociate any remnant molecular material that remains into the planetary nebula stage. And so on the screen here, I'm showing a sampling from the model of Redmond et al., which was published back in 2003. So it shows abundance on the y-axis with respect to molecular hydrogen and nebular age on the x-axis, and showing the predicted abundances for several different molecular species, specifically HCN, HNC, HCO+, and CCH at 3 different points along this 10,000 year span. And so in all of these cases, these abundances are pretty significantly depleted. So for instance, HCN, which is shown in red here, is depleted by about 6 orders of magnitude over the course of about 4,000 years, according to this model. And so what this indicates is that molecular material might be so significantly depleted by the end of the planetary nebula stage that it may not be a significant supplier of this material to the interstellar medium. So in order to determine whether planetary nebulae could be potential sources of molecular material for the interstellar medium, over the past several years, I have undertaken several molecular surveys of these objects, starting from my time as a graduate student at the University of Arizona. And initially, I drew from a sample of 17 target sources, which are shown here, in which CO had been previously detected, but few to no other molecules had. And these sources were diverse in a variety of ways, but the most important way in which they were diverse was in terms of their nebular age. They ranged from the young to the old. And this allowed us to explore how molecular abundances varied over the nebular lifespan and how that compares to the predictions of chemical models. So each of the surveys that I performed were undertaken using the facilities of the Arizona Radio Observatory shown here. And so this includes the 12-meter telescope on Kitt Peak and the sub-millimeter telescope on Mount Graham. And using these telescopes, my colleagues and I observed transitions of various species, which include those of HCN, HCO+, HNC, and CCH, which were the molecules I highlighted from the Redmond survey before. Each of these surveys was quite successful. So at least one transition of HCN or HCO+ was detected in about 76% of the 17 nebulae that we targeted. And so some of the sample spectra from these surveys are shown to the left here, which includes various transitions of CO, as well as the J = 1 to 0 and 3 to 2 transitions of HCN and HCO+. HNC and so here are some sample spectra from the HNC survey, was detected in 100% of the 11 nebulae that we targeted. And these 11 nebulae were those in which HCN had been identified. And CCH, some sample spectra are shown to the left here, were identified in 82% of these 11 sources. And so we specifically targeted those sources in which HCN had been observed because this implied that these objects might be carbon rich and thus a source of other carbon containing molecules. So several remarkable results came out of these studies. So to the left here, we have a plot of abundance relative to molecular hydrogen versus nebular age as before. So here the circles are showing our data color-coded according to the molecule in question, and the model predictions from Redmond et al. Are shown in triangles here. And so this plot shows that in contrast to the predictions of this Redmond model, molecular abundances stay pretty consistent over this 10,000 year time span. And another interesting thing is that these abundances are consistently on the order of 1 to 2 orders of magnitude greater than those measured in the diffuse interstellar medium. And ratios of various species like HCN to HNC are also consistent with those that are measured in diffuse clouds. And so putting this all together, this paints a compelling picture that not only can molecules survive the planetary nebula stage, but they can potentially also explain the molecular abundances measured in the interstellar medium. In other words, the molecules that we see in these diffuse clouds could be ejecta from planetary nebulae. So recently, we've initiated another search for HCN and HCO+ in an additional 13 planetary nebulae in order to expand the number of sources in which molecules beyond CO and H2 have been observed. And so some images of these 13 nebulae are shown here. There are a couple of sources that I'm looking at that are not pictured. So far, this survey has been a great success. We have detected HCN in 10 sources so far, and HCO+ in 11, and we're still finishing up these observations, but hope to be done soon, and we're looking forward to publishing these results. And so some sample spectra from the study are shown to the left here. So even more remarkable findings have come out of this work, and one of the most remarkable of these involves a seemingly unremarkable planetary nebula called K447. So K447 was one of the original 17 planetary nebulae that were targeted by the original molecular surveys that I talked about just a few minutes ago. It's a young planetary nebula with an estimated age of about 900 years. And prior to the observations I'll talk about in just a moment, it had been detected in various molecular transitions, including those of CO, CS, HCN, HCO+, HNC, and CCH. So the source we thought was worthy of further study. And as a result, we continued observations of this nebula using the ARO facilities that I showed earlier. And these observations revealed an unusual enhancement of rare isotopes, so specifically those of carbon-13, nitrogen-15, and oxygen-17. And so specifically, we observed these isotopes in the form of H13CN, the spectra of which are shown here, HC15N, the spectra of which are shown here, 13CS, and C17O. And I'll discuss, I guess, the comparisons between these spectra and those of the main isotope in just a moment. But in addition to these ARO observations, we also performed additional observations using the IRM 30-meter telescope in Granada, Spain. And those observations revealed a treasure trove of molecular species. And so some examples of our IRM survey are shown to the left here. Some of the spectra that are shown to the right over here that I'm trying to circle with my cursor are also additional ARO observations. And combining our ARO and IRM observations, we've identified over 30 different molecular species and isotopologues in this source with various carbon-bearing species, which indicates that this source is extremely carbon-rich. And this makes it one of the most, if not the most, molecule-rich planetary nebulae known. Some of the species that we detected in this object, like CH3CCH and CH3CN, had not previously been detected in planetary nebula before. And we also detected many other carbon-13 bearing species, and this includes singly and doubly substituted forms of HC3M. So in the spectra to the left here, it's kind of tiny, but I've highlighted some HC3N lines as well as some singly substituted HC3N lines and some doubly substituted HC3N lines as well. So that indicates that there's an extreme carbon-13 enhancement in this source. And so by performing radiative transfer modeling on these observations, we were able to ascertain a carbon-12 to 13 ratio by comparing the abundances of these carbon-13 bearing species to the corresponding carbon-12 bearing species. And numerous molecules, everyone that we looked at pretty much confirmed that there's a carbon-12 to 13 ratio of about 2 in this source. And so going back to those other observations that I showed before of HC15N and C17O, radiative transfer modeling has indicated similarly low nitrogen 14 to 15 and oxygen 16 to 17 ratios in this source of about 14 and 21 respectively. And with the latter two here, these are the lowest values yet measured in interstellar gas. And so these ratios are particularly notable when you compare them to solar system values, which are about 90, 400, and 2600 respectively. And so since these observations, we've performed additional observations of carbon-13 bearing molecules like 13CO, H13CN, and H13CO+ in 8 other planetary nebulae. And these observations have revealed similarly low carbon-12 to 13 ratios of on the order of 1 to 13. And several of these ratios are lower than the minimum value that's achievable in equilibrium CNO burning. And these nebulae that we observed represent a mix of both carbon-rich and oxygen-rich sources. So the suppression of carbon-12 to 13 that we observed in these sources, as well as in K447, are in line with previous observations of carbon-12 to 13 in other planetary nebulae, which range from about 2 to 40. And to understand why these ratios are so unusual, I'll briefly recap how carbon-12 and 13 are generated in evolved stars. So carbon-13 is produced on the red giant branch as an intermediate product of hydrogen shell burning in the CNO cycle, and it's convectively mixed up to the surface during first dredge-up. Carbon-12 is generated through the triple alpha process on the asymptotic giant branch and is brought to the surface during third dredge-up. And so in this process, the carbon-12 to 13 ratio rises from about 10 to 25 on the red giant branch to over 30 on the asymptotic giant branch. And in this process, the star can be converted into a carbon star. And so this is consistent with carbon-12 to 13 ratios that have been measured in AGB stars. So typical carbon-12 to 13 ratios in oxygen-rich stars are about 5 to 30. And typical values for carbon-rich stars are about 34 to 150. And this is consistent with, well, the values in oxygen-rich stars, I should say, are consistent with the carbon-12 to 13 ratios that we measured in our oxygen-rich planetary nebulae. However, the extremely low carbon-12 to 13 ratios in our carbon-rich planetary nebulae present a conundrum because those are not consistent with those that are measured in carbon stars.
2 minutes.
Thank you. And so in order to explain this extreme carbon-13 enrichment, as well as the extreme nitrogen-15 and oxygen-17 enrichment that we saw in K447, we considered several possibilities. So one possibility is that the progenitors of these carbon stars the progenitors of these carbon-rich planetary nebulae could be J-type stars. And so these are carbon stars that have very low carbon-12 to 13 ratios. The problem here is that these only comprise about 15% of the AGB population. And so statistically speaking, then we'd only expect 2 of the peony in our sample to have J-type progenitor stars. Another explanation for these very low carbon-12 to 13 ratios are that they could be created through hot bottom burning, which is when the convective envelope dips down into the hydrogen burning shell and it dredges up carbon-13. But the problem is that first, this process only occurs for stars that are greater than 4 solar masses. And to our knowledge, only 2 of our targets meet this criterion. And then another issue is that this process can also change a carbon-rich star into an oxygen-rich one. And so that couldn't explain the suppressed ratios that we observe in our carbon-rich nebulae. And so another possibility involves an explosive process that occurs at the AGB to PN transition. And so specifically, an explosive helium shell flash, which is potentially driven by dipole oscillations that can occur in stars during helium burning, could create an explosive bipolar expansion. And this flow could drive helium and carbon from the helium shell into the bottom of the hydrogen zone, where this hot hydrogen can react with carbon in order to produce carbon-13 through hot proton addition, which is what's shown in this reaction here, as well as nitrogen-15 and oxygen-17 through the reaction shown on the screen here. And this explosive process could then eject this material from the star and potentially produce the extreme bipolar outflows that are observed in many of the planetary nebulae in which we've detected these extreme enhancements. And I'm showing some images of these sources to the left here, which indicate this extreme bipolar outflow. But of course, further explanation of this possibility is needed, and we're performing further isotopic study of other planetary nebula as well. And yeah, that's it. Thanks so much for listening to my talk, and I'd be happy to take any additional or any questions with my remaining time. Thank you.
Thank you, Debbie. That was a very interesting talk. Some people are clapping as well. If you have any questions, please raise your hand via the reactions button. Ooh, many questions, well, many claps, and a question by Sophia. Please go ahead.
Thank you, and thank you for this interesting talk, Debbie. I was wondering, how do you derive the isotope ratios from the isotopolog ratios? Because yeah.
Oh, I'm so sorry.
Yeah, go ahead. I'm sure you got my question.
Yeah. So the way that we do it is, I'll just go back to the K447 slide here as an example. So we have observations of HCN in this source, as well as H13CN and HC15N. So what we've done is we performed radiative transfer modeling to determine column densities for these three species. And then we just compare the column densities of these three species to one another to estimate a carbon-12 to 13 ratio or nitrogen-14 to 15 ratio, because the only difference here is just in terms of one has carbon-12 and the other has a carbon-13 substituted. I'm not sure if that addresses your question. Does that make sense?
Well, that certainly answers my question. Yeah, I'll ask something more in the Slack channel. Thank you.
You can go ahead and ask now as well, Sophia. I don't see any hands.
But I think I'll stick to Slack. Thanks.
Okay. You have the option. In that case, I'm going to ask a question, so that works in handy for me. Do you know anything about the temperatures of the stars in the planetary nebulae? So is there a correlation with the white dwarf temperature?
Yeah, that's an interesting question, because we did look into this in our HNC survey. I'm sorry, it was in our CCH survey, because we were trying to see whether there was a correlation between the presence of CCH, or some of the sources we looked at had C60 detected. So we wanted to see if there was a correlation with central star temperature in terms of the presence of C60 versus CCH. At any rate, we do have information, and they seem to be hotter stars. I think all of them are greater than 70,000 Kelvin, if I'm remembering correctly. And I think the hottest one might be something on the order of 130,000 Kelvin.
Okay.
I do have that information. I just don't remember off the top of my head.
No, sure.
Yeah.
Thank you. It's interesting. Does anybody else have a question? Greg has a question in the chat. I will read it out, or you can ask it live, Greg.
I could read it. This is the most basic of questions, Debbie. I was just wondering, when you say that a planetary nebula is so many years old, that would be so many years after what happened?
So that would be, that's actually a good question, because I want to say after the initiation of the planetary nebula stage, but what does that mean? I mean, so my understanding would be, it would be after the, it's a good question.
We could take it offline, because I was just thinking that might not be so easy to define. Basic, but not easy. It's all right. You'll see why I'm curious when I talk this afternoon.
Yeah, no.
Interesting. All right. Are there any other questions? Theo, yes, please go ahead.
Hi, thanks, Debbie, for a nice talk. So this explosive nucleosynthesis processes that process that you propose that can explain these isotopic ratios, is it something, I don't know if I missed it or if you didn't say, is it something that can just happen naturally, or do you expect some kind of specific cause?
Like a trigger for?
Yeah, exactly.
That's a good question, and I will admit that I probably don't have the answer to it, mainly because this is a little bit, I mean, one of my colleagues is the one who's the driving force behind this proposition. And so I don't know if it would necessarily require a trigger to occur. So I guess the point is that I don't really have an answer to that question. I'm sorry.
Okay, no problem. Thanks.
Okay, thank you again, Debbie, for the very interesting talk. Our next speaker has not shown up. Yes, difficulties connecting. It was bound to happen, right, on a virtual conference. So, well, consider this. Hopefully it's the only one. Hopefully everything else will go smooth in the remaining, in today and tomorrow. So this means that we have a slightly longer break, which is also nice.